Section 2.6 is all about proofs about segments and angles. This is just a continuation of last section when we were introduced to the proof process, but we did the proof process with algebra problems that were familiar. This is your formal introduction to what proofs are when it's beyond just algebraic proofs. So let's first look at the formal definition of what a proof is. A proof is a logical argument that shows a statement is true. There are several different ways to organize your proof. Your book talks about 3 of them. The first one is called a flow chart. So you kind of start off with the main idea and you have ideas that come off of it, and then you might have more ideas off of those, and it just keeps flowing like that. Another way to organize your proof is just called a paragraph proof, where you literally just write a paragraph stemming one statement to the next and giving reasons for each statement as you go through the proof until you finally prove whatever you want to be proven. The way that we will write our proofs is called a 2-column proof. A 2-column proof has numbered statements and corresponding reasons that show an argument in logical order. The left-hand column is for the statements, and the right-hand column is for the reasons. We saw this in the last section when we did our algebra proofs, where we solved the problem in the left-hand column and then justified each step in the right-hand column. The right-hand column can include postulates, definitions, properties, and theorems. Now remember, the difference between a postulate and a theorem is that postulates are things that cannot be proven. They are things that we just know are true, and theorems can be proven. So again, all of these are fair game for reasons that we can list to justify the statements in the left-hand column in our 2-column proof. Here's a nice graphic that I found from your textbook that summarizes what a 2-column proof is. So when you're writing a 2-column proof, you make one statement at a time until you reach the conclusion. Because you make statements based on facts, you are using deductive reasoning. Usually the first statement and reason pair you write is given information. This was stated in the last section of notes when we did the algebraic proofs, that you always start with what is given. The rest of this graphic shows you how to set up a proof. You can see here they are given that angle 1 is congruent to angle 2, so this diagram right here, and you're supposed to prove that angle 2 is now congruent to angle 1. So you can see they set it up. Here's the left-hand column with the statements and the right-hand column with the reasons. We were given that angle 1 was congruent to angle 2, so that was the reason. So here are the statements on the left-hand side, the statements based on facts that you know or conclusions from the deductive reasoning that you were doing. And you notice that they're also numbering each step in the proof. Each step in the proof is numbered, and it's paired with a numbered reason on the right-hand column. So remember, each time you make a statement, you have to give a reason for that statement. And all of these in the right-hand column have to be definitions, postulates, or proven theorems that allow you to state the corresponding statement. So again, this gives you a nice visual of how to set up and write a 2-column proof. Example number 1, 4 steps of a proof are shown. Give the reasons for the last 2 steps. So the given information is that AC is equal to AB plus AB, where you're supposed to prove that AB is equal to BC. So here's our diagram. We are told that from A to C is equal to AB plus AB. And we're supposed to prove that AB is equal to BC. So you can see they started the proof with the given information. We were told that AC is equal to AB plus AB, and the reason was given. We then state that AB plus BC, so AB plus BC is equal to AC. That postulate was given to us in the first chapter. It was called the segment addition postulate. The segment addition postulate just said if you have 2 smaller segments making up a bigger segment, we can add those 2 smaller segments together and it would be equal to the big segment. Now, if you look at our first 2 statements, we see that AB plus AB is equal to AC, and we also see that AB plus BC is equal to AC. So this AC is linking those 2 statements together. So now we can state that AB plus AB is equal to AB plus BC because they were both equal to AC. Thinking back to the last section where we talked about reflexive, symmetric, and transitive properties, remember it was the RST 1, 2, 3, where you counted out the number of equal signs. If we count the number of equal signs here, we have 1, 2, 3. So that would be the transitive property, allows me to state that AB plus AB is equal to AB plus BC. So notice I now put the transitive property as my reason for step 3. Step 4 says AB is equal to BC. Looking back at step 3, we have an AB on both sides of the equal sign. Knowing that we can subtract the same number from the left side of an equal sign and the right side of the equal sign, I'm basically just subtracting the AB and the AB on both sides, so that would be the subtraction property that allows me to now state that AB is equal to BC. So as you can see here, I now stated that the subtraction property is the reason for step 4. Now remember, we were asked to prove that AB is equal to BC. Notice that is the last step in my proof. Your last step in your proof should always be whatever you were told to prove. So like the prove statement in your problem should always be the last statement in your 2-column proof. To show that we are done with this proof, remember we use the 2 lines indicating that the proof is done. This graphic links the reflexive, symmetric, and transitive properties that we talked about in the last section now to the congruence of segments and the congruence of angles. If you remember from the last section, the reflexive, symmetric, and transitive properties all had equal signs in them, and now we're just saying it's still applicable, the reflexive, symmetric, and transitive properties, even though now we're using congruence rather than equal signs. So the reflexive property is still that a segment is congruent to itself rather than a number is equal to itself. The symmetric property states that a segment that is congruent to another segment, I can flip that around and it'll still be true. And the transitive property states that if I have a segment congruent to another segment and that same segment congruent to a different segment, that the original segment and that new segment are still congruent. The same thing is applied to angles. Angle is congruent to itself. I can flip it around and it's still true. And if I have angle A congruent to angle B and B to C, then A is also congruent to C. So again, this is just more of the same from the last section. We're just now relating it to congruence rather than equality. Example number 2 wants us to name the property illustrated by each statement. Part A, if angle RST is congruent to angle MNP, then angle MNP is congruent to RST. So you can see here that angles were just flipped around. Looking back at that last graphic, whenever I flip something around and I have 2 equal signs or 2 congruent symbols, that is the symmetric property. In this case, it would be the symmetric property of congruence, but rather than the symmetric property of equality like it was in the last section. But if you just write symmetric property and don't state it is of congruence, I'll still know what you mean. Part B says if segment AB is congruent to segment FG and segment FG is congruent to segment MN, then segment AB is congruent to segment MN. So we can see that the FG is linking A, B, and MN together. And if we count up the equal signs, or in this case congruent symbols, we have 1, 2, 3. So RST 1, 2, 3. This would be the transitive property. Again, this would be the transitive property of congruence. If you don't state that, I will still know what you mean. So it's just sufficient for you just to say transitive property. Example 3, if you know that M is the midpoint of segment AB, N is the midpoint of segment CD, and that AB is equal to CD, prove that AM is equal to CN. When I start these problems, I like to first mark on my diagram the information I was given in the problem. So in this case, I was told that M is the midpoint of segment AB, so that means I know AM is congruent to MB. And I also know that N is the midpoint of segment CD, so that means that CN is congruent to ND. This gives me a nice visual of what I know and what I don't know. I know that I need to prove AM is equal to CN. So when I finish my proof, that should be the last thing that is stated. The first step in any proof is to write down what you were given. In this case, we were given that M is the midpoint of segment AB. We also know that N is the midpoint of segment CD. And we also just know that AB is equal to CD. And we know that because it was given. Remember, the first step is to always write down the given. Next, let's write down what we know because we have those midpoints. We know that AM is equal to MB and CN is equal to ND. We know that because we were told that we have 2 midpoints. The definition of the midpoint tells me that it bisects a segment into 2 congruent segments. So my reason is just that we had a midpoint, so it's a definition of a midpoint. Remember, you can use definitions as reasons in your right-hand column to justify your statements in the left-hand column in your proofs. Next, we have a couple other things we know. We know that AM plus MB is equal to AB, so the two smaller segments added together equals the bigger segment. And we also know that CN plus ND is equal to CD. Same thing, two smaller segments are equal to the bigger segment. We know that because of the segment addition postulate. Okay, and then step 4 is where we'll start moving some stuff around. If we look at our previous two steps, we see that AM is equal to MB and CN is equal to ND. So I'm going to substitute AM equals MB. I'm going to put AM in for the MB right here and the CN in for the ND down there. So now I know that AM plus AM is equal to AB, and I know that CN plus CN is equal to CD. I know that because I substituted what I knew about AM and MB and CN and ND. So that was the substitution property. Next, I'm just going to combine the AM plus the AM, so that's 2AM equals AB. And CN plus CN is 2CN. Believe it or not, doing that is actually the reversal of the distributive property. When I combine like terms like that, that's actually just the reversal of the distributive property. So step 5 would be the distributive property. So now looking back at my problem, I see that I have AB is equal to CD. So if I have 2AM equal to AB and 2CN equal to CD, knowing that AB and CD are congruent, I know that step 6, 2AM is equal to 2CN because I substituted the 2AM and for the AB and the 2CN and for the CD into this statement up here. So my reason would be the substitution property. So finally, if I just divide both sides by 2, I would end up with AM equals CN. Again, that's the division property because all I did was divide both sides by 2. And notice that was what we were supposed to solve and prove all along. AM is equal to CN. So now I have proven that AM is equal to CN given all of our information. So this proof is done. Now I know this can be confusing and tricky and something you might be having anxiety over, but there's no need for it. We'll obviously get better at this as we do more and more examples. But as always, make sure you write down any questions so we can cover them in class, and we'll see you then.